For decades, the technology industry has reliably doubled computing power every 2 years by shrinking the size of transistors. This physical scaling relies on a classical assumption that energy and voltage flow in a smooth, continuous stream. We are now approaching a physical threshold where a single transistor is roughly the size of an atom. At these microscopic dimensions, the mechanics of continuous flow break down entirely. The data showing this breakdown is not new. It was first documented in 2 physics experiments conducted over a century ago. To understand why modern microchips are hitting a hard physical wall today, we have to examine the 19th century data anomalies that broke classical physics in the first place. In the late 1800s, the scientific consensus held that electromagnetic energy operated exclusively as continuous waves. Under this model, the amount of power delivered by a wave was dictated entirely by its intensity, or amplitude. This mathematical framework reliably explained large-scale engineering problems, but it produced severe calculation errors when applied to microscopic phenomena. Continuous wave equations break down at the atomic scale, yielding mathematical results that are physically impossible. The first major breakdown happened with blackbody radiation. Hot objects naturally emit electromagnetic waves based purely on their temperature. This graph compares theoretical predictions against actual data. Classical theory, the blue curve, predicted that as wavelengths decrease toward the ultraviolet, energy climbs infinitely. But measurements showed something else. The red experimental curve demonstrates power output dropping sharply at small wavelengths. This power spectrum chart maps intensity as a function of wavelength. As an object's temperature increases from 3000 to 6000 Kelvin, total power output rises, and the peak intensity shifts sequentially toward smaller wavelengths. To reconcile the mathematics with these physical measurements, physicist Max Planck proposed a theoretical fix. Charged particles could only emit light in specific, non-divisible portions. He called these discrete portions quanta. The energy of each portion is determined by multiplying its frequency by a set constant. Energy does not scale on a smooth, continuous ramp. It operates on a strict staircase of distinct values. Planck's mathematics were highly abstract until a specific mechanical experiment proved they were a physical reality. This was the photoelectric effect, where light strikes a metal surface and ejects an electron. Classical physics assumed that shining a high-intensity light of any color onto a metal plate would eventually deliver enough cumulative energy to break an electron free from the surface. Researchers tested this using the setup shown in this diagram. Light entering the vacuum tube strikes a cathode plate. But the results contradicted classical expectations. Intense red light ejected 0 electrons, yet faint blue light caused an immediate current to flow. Looking at the internal mechanism in this schematic, scientists applied a stopping potential voltage to the negative electrode. This allowed them to measure the exact kinetic energy of the electrons moving across the gap. The sheer volume of incoming light was irrelevant. Triggering the atomic reaction was strictly gated by the light's frequency. This graph plots the stopping potential against the incident frequency for 3 different metals: sodium, iron, and platinum. Notice where the red lines intersect the horizontal axes. These precise points represent the absolute minimum frequency required to cause a photocurrent in each specific metal. That intercept defines the metal's work function. It is the strict minimum atomic binding energy that incoming light must overcome to remove a free electron. Albert Einstein synthesized these observations by proposing that light itself travels as individual quantized packets, photons. Each photon interacts on a strictly one-to-one basis with an individual electron. If the energy of a single incoming photon is lower than the metal's work function, the electron will not be ejected, no matter how many trillions of photons strike the surface simultaneously. Matter and energy only interact through discrete, indivisible transactions. The classical continuous wave model could not survive this data. We apply this hard physical limit to the modern computing hardware printed on this silicon wafer. Integrated circuits calculate data by moving electrons across physical barriers to register binary ones and zeros. At macroscopic scales, this behaves like a continuous flow of water regulated by a physical gate. At the width of a few atoms, the transistor gate functions as an energy barrier, governed by the exact work function. These discrete quanta were first measured over a century ago. At this scale, electrons can tunnel through barriers or fail to jump them entirely. Unpredictable quantum effects dominate the environment, preventing reliable binary switching. Moore's law is stalling. We have not run out of engineering ingenuity. We have collided directly with the absolute quantum thresholds of matter. Because you cannot scale a continuous flow transistor past this quantum wall, the technology industry has had to pivot its entire manufacturing strategy. Instead of pushing for further miniaturization, modern hardware development relies on vast parallelization, packing more cores and multi-thread architectures into processors to maintain speed. To achieve the next major leap in computational power, we have to build quantum computers. These systems abandon classical binary frameworks entirely, electing to natively compute using those exact discrete quantum states. Mathematical limits identified in a laboratory in 1900 perfectly mapped the absolute boundaries of 21st century hardware. The end of Moore's law represents the exact moment human engineering finally reached the physical constraints of a quantized reality.